Hello, students. Today we would like to talk about another method for combining functions. We spend a lot of time working with functions in this class, adding functions, subtracting functions, multiplying, dividing. We transform them. And in many cases, the first thing we do with every problem is compute the domain. In some instances, we're able to actually compute the range. We will see that the computation of range will be aided by some of the techniques that we will learn in the calculus. So today we want to talk about another method for combining functions. This is called composition. That is, the composition of two functions produces another function. And we will find as we continue the study of mathematics and STEM that the composition will be very useful to us. So let me share my screen. Again, just like the first time we started multiplying and dividing functions, we weren't really sure, okay, so we know how to do this, where is it important? As you do other types of problems in science, mathematics, engineering, you find that it is very convenient to be able to combine functions. And we will certainly find that the composition of functions will be extremely important to us. So when we use the phrase composition, what do we mean by that? As I've written here, I've got suppose f and g are functions. The composition of f and g is written with a 0 or lowercase o, if you speak. F composed with g, or sometimes written the composition of f with g, is f of g of x. And you're thinking that's pretty simple. The idea is that the outer function is the first function that we write, the function to the left. And the function to the right is called the inner function because what we do is we substitute g into f. Again, f composed with g is f of g of x. And as I've written in red here, we often call the left function the outer function, and we call the right function the inner function. Now, we will adhere to this methodology. That is, often books will reverse ideas between F and G. It really depends on the author, but we will always have the outer function on the left and the inner function on the right. So it's very easy to go from F circle G to f of g. We maintain that order. Now, even though I have the domain written here, this is a tacit assumption based on how we've defined the composition of two functions. That is, the domain must start with the inner function. That is, the x must be in the domain of g. And then if we're substituting g of x into f, g of x must be in the domain of f. That is, for every x in the domain of g, g of x must be in the domain of f. And what I've written here is the order can change. For instance, maybe you want g to be the outer function and f to be the inner function. You certainly would have no reason to think that they would be equal. And in many instances, they are not equal. That would be an assumption that would be actually true. Compositions are not equal when you rearrange the order of the inner and outer function. So again, the order, the labels on the functions, that is something you can dictate if you are making up the problem and defining your own functions. So let's look at an example. I started out with a simple one just so that we could get practice not only computing a domain, but also computing the actual formula. And I'll give you some options. The composition is not difficult to master, but there are certain things that you can do to avoid careless mistakes. So the outer function f will be 1 divided by the square root of x plus 1. The inner function will be g of x, which is the polynomial x squared minus 5. Now, again, remember, when we compute domains, we are looking at real valued functions of a real variable. So we're looking for the largest set of real numbers for which the function is defined. So we're not making any restrictions unless we decide that there should be restrictions on the problem we're creating. So as we look at g of x is a polynomial. It is defined for all real numbers. So we have a very simple task of computing the domain of g. And now, if we follow the definition here, g of x must be in the domain of f. So we think of the substitution process. Everywhere we have an x in f of x, we substitute g of x. So that means, in this particular case, that x squared minus 5 plus 1 must be greater than 0. Notice the radical is in the denominator, so the argument cannot be 0. But in order for the square root to be defined, the argument must be positive. So that says that x, which in this case, when we replace it with x squared minus 5, x squared minus 5 plus 1 must be greater than 0, or equivalently, x squared minus 4 must be greater than 0. Now, what I've done here is remark about two different ways that we can do this. There is no x term, so we have flexibility on how we can solve this inequality, and that is completely up to you. The first technique is just to think about BVs, because of course this is a difference of two squares. And so we can write this as x minus 2 times x plus 2. And of course, this must be greater than 0. So now, of course, we look for the BVs. Where can these particular factors be 0? Well, at 2 and negative 2. So we have BVs of 2 and negative 2. Now, of course, we can plot these, and of course, this is completely factored, so it's easy to analyze. Both of these factors have multiplicity 1, so if you think of an extreme value of like 100, then of course you get a plus or a positive sign. And then, of course, at the 2 and the negative 2, with multiplicity odd, we must cross, so we go from positive to negative, negative to positive. So now we can see that for this region, greater than 2, we have the positive. And for this region, less than negative 2, we have the positive, which will satisfy this. So now when we write the domain of the composition, again, we have to intersect with the domain of the inner function, but that's very easy. It's just all real numbers. So all we have is just this restriction that we've computed here. So now we know that x must be between negative infinity, negative 2, union 2 to infinity when we think about where x will live. And then, of course, we can write formally the domain of f circle G will just be negative infinity to negative 2, union 2 to infinity. Again, using the parentheses here because we do not want to divide by 0. So again, you look at this and think, well, the alternative would be to actually compute the actual formula for the composition and then see what restriction would result there. And that's a fine way to do it. Note that since we are actually building the function from two functions, we must always be aware of the domain of the inner function, because disregarding that will impact the actual domain. Because again, we think of the process of building, x is substituted into g of x is substituted into f of x. So there are two domains that must be satisfied. So we can't just forget the domain of the inner function. Let me show you what I mean. And before I do that, recall that if we don't have the x variable, that is x in first degree, we can simply transpose and then apply the square root function, which is an increasing function, and then get the square root of x squared, which is the absolute value of x, to be greater than 2. And of course, this is the disjunction, which gives you exactly this using properties of the absolute value. So if you want to go this route, that is certainly fine. We do a lot with BVs. They're very useful. And so if you would rather factor, you can do that too. Both of these work fine, and it is your choice as to which method you would like. Now, I wanted to show you an example. Again, go ahead and finish the last example and then look at another one that will showcase exactly what I'm talking about. And then we'll do an interesting problem with another factorization. Note, if we wanted to go ahead and compute the actual formula for the composition, we can say f circle g of x. Again, I've repeated f and g here. So we have f of g of x by definition, and then I just replace g of x with x squared minus 5, and then, of course, do the substitution, which looks very familiar with what we did last time. So now if you notice this, and you just started with this function, then you'd be okay. You would apply the domain computation to the x squared minus 4, necessarily having to be positive or greater than 0, and get the same result. Again, the domain of definition for G is all reals. So even if you forgot about G, it would not impact the actual domain of the composition. So again, when we're building the function, we can't forget the inner function. If we just start with the function and we analyze it like we've been doing before we even knew the definition of composition, then you're fine. You just have to remember, are we building this from two functions, or are we just given a single function for which we compute the domain? So I think when you break it down based upon the definition, you're less likely to forget. So I point that out as being more of a means to remind yourself about what's going on so that you don't make careless mistakes. Now, the next example basically illustrates what I've been talking about. It's not as difficult as the first because we don't have the factorization that's required. But notice, f of x is 2 divided by x minus 3. G of x is 1 divided by x plus 4. And this particular example is from your lecture notes. It's problem number 2. And so what I've done, I've added an additional idea that we need to do. Let me just check the focus here. Looks good. So we start with the inner function. That is, we see that the inner function would omit -4 in the domain because that would ensue division by 0. So when we have the domain of G, we don't get all real numbers as we did in the last example. We just have all real numbers except -4. So using the interval notation, which is somewhat long-winded, this does exactly what we need it to do. Now, using the definition of composition, we now replace x in the outer function with 1 divided by x plus 4. But now as we look at f, the variable in the denominator would require that x minus 3 be non-zero. So when we make the substitution, this simply says 1 divided by x plus 4 minus 3 does not equal 0. Now, this is not hard to do because, again, it's just an inequality in the sense of a not equal to. So we don't have to be as formal about signs because it would never cause us a problem. So let's go ahead and transpose. So we have 1 divided by x plus 4 is not equal to 3. And then, of course, if you like, you can reciprocate or cross multiply. So if you cross multiply, you'll get a 3x plus a 12, 1 not equal to 3x plus 12. And then, of course, if you transpose the -12 with the 1, you get the -11. So 3x is not equal to -11. Divide by 3, so x is not equal to -11 divided by 3. And then, of course, if you wrote that as a mixed number, 3 divides -11 -3 times with 2 left over. So you get -3 and 2/3. Okay, so and the reason I did this is because we just need some comparison to the number -4. We see that -3 2/3 is larger than -4. So when we write our domain with the intersection, we must what? Omit -4, and we also must omit what? -11/3. If you choose to write it this way as the improper fraction, that's fine, or you can write the mixed number. I think this would probably be more customary. So now the domain of f composed with g would be -infinity to -4, union -4 to -11/3, union -11/3 to infinity. So again, it's important to realize that you're building the function, because if you neglected the inner function and you simply focus on the restriction by substituting the inner into the outer, then you necessarily leave out the -4. So let me illustrate what I'm talking about. For instance, if you just went ahead and did the formula. So if we actually wrote the formula for the composition of f with g, we would now do just like we did here, but notice we have f of 1 divided by x plus 4. So now we just look at our f function. So that means we have 2 divided by 1 divided by x plus 4 minus 3. And then at this point, of course, that's valid, but it's a little bit untidy. So we'll just not choose to leave it as a complex fraction. So at this point, we just get a common denominator. So we have, in this case, 1, again, this starts to look very familiar, -3 times x plus 4 divided by x plus 4. So this will give us the 1 minus 3x minus 12. Again, the -12 and the 1 give us the -11. All looks very familiar. And now if you like, we'll just, what's division by fraction? Reciprocate and multiply. So we have 2 over 1 times x plus 4 divided by -3x minus 11. Now, if you like, you don't like all these negatives, we can go ahead and factor the negative, and we just have 2 times x plus 4 divided by 3x plus 11. So now, of course, when we look at this, we simply see that these are related. That is, we would get the x not equal to a -11 over 3 just by looking at the denominator here. But now, if you simply focus on this, you would see that the omission of the -4 would not be evident here, because when you reciprocate, now the x plus 4 is in the numerator. But just recall, when we built this function, this was the inner function. So this is what I'm commenting on. If you're building the composition with two functions, then you must always remember the domain of the inner function. And here, that omits the -4. So we have to remember that it depends on how the question is posed to us. If we're just asked to get the domain of this as a single function, it would exclude that number. But if we build the function as a composition, then not only would we exclude this number, but we would also exclude the -4. So that's a subtle point. And in most applications, it would depend on the scenario. Okay, are you building the function? Maybe you're creating a function, you're building it from two functions. It just depends on the scenario that you're working with. So keep that in mind as you do these examples. Now, the last example, I just wanted to throw in some factorization so we could get a little practice with that. So I've made this one up. We have h of x. Use any letters you like, ladies and gentlemen. It doesn't matter. We have the square root of x plus 3. And then we have g of x equals, it's a polynomial, quadratic, x squared plus 4x minus a 5. Now, like I said before, in general, if we switch letters, that is, if we said h circle g of x, in general, this would not be equal to g circle h of x. That is, now if you interchange the role of the inner and outer function, there's no reason to ever believe that this would ever be true. But there will be a situation where this will actually be valid, and that will be in the case when we have one-to-one functions. And that's what I'll talk about in the next lecture. That'll be a very important point where we define the inverse function. So for now, in general, this is true. There would be no reason to believe that these would be equal. So keep that in mind, and then also keep it moving around in your brain. When we get to one-to-one functions, there'll be a very specific outcome that will help you understand why we can actually define inverse functions. So now what we want to do is compute the domain of H circle G, and then compute the actual formula, H circle G of X. So again, if we apply the routine of looking at the inner function and then the outer function, I think we'll have better success. But you can see here that for this particular polynomial, the domain is G. I just want to get some practice with factorization. So domain of G in this case is all real numbers. It's just a polynomial. And notice now we have to substitute G into H of X. We have one occurrence of X. So that means that we now have another inequality. That is, we have X squared plus 4X minus 5 plus 3 must now be greater than or equal to 0. Now, of course, if you have more occurrences of X, you just have more algebra. It doesn't change the definition. It may take a little bit more maneuvering to clean up the function, but that again is just part of the process of looking at different examples. So now, of course, we can just add the -5 and the 3 and get a -2. So we have X squared plus 4X minus 2 is greater than or equal to 0. So notice now, again, with the last problem, we excluded the 0 because the radical is in the denominator. So now what we're seeing with compositions, this is exactly why we've done the BV techniques, why we have understood inequalities, because with compositions, we necessarily are forced to deal with domains and also inequalities just by virtue of the fact that we have radicals in our algebraic functions. So now notice, of course, Gauss's lemma would say that this does not factor over the rationals. We know if we can get the rational factorization, then we have the integer factorization, but the AC method pretty much leaves that out. So let's look at the discriminant, b squared minus 4ac. So we have 4 squared minus 4 times a times c. But of course, we have the minus minus, so that gives us the plus. So this will equal 4 squared plus 4 times 2. And of course, we can factor the 4. It's a perfect square. And we just get 4 plus 2. So this is just 4 times 6, which is clearly positive. So this implies 2 distinct real numbers. So what's interesting about whatever new objects we define, we continue to do the same techniques. We factorize, we use number theory, and then we use BVs to solve inequalities. That will be what you will continue to do through your STEM mathematics and also in your other STEM classes, because the real analysis and even the complex analysis is very important when it comes to figuring out signs. Well, I'll just say this. The complex numbers are not ordered, Okay, so when I say that we're dealing with order in the real numbers with the BVs and the inequalities, that's very important, but we still have the concept of absolute value in the complex variables. We call it the modulus. We still have to deal with the algebra, but just very unique to the real numbers, since it is a beautiful field, a continuum that is ordered. It is the perfect setting for calculus. So even though we don't have the order in the complex number system, we certainly have the elegance that we've come to enjoy with the real numbers. So now we can use our quadratic formula. X is equal to the opposite of b, so we get a -4 plus or minus. Now we have the square root of 4 times 6, so that's 2 square root 6 divided by 2a, so 2 times 1. So again, we're focusing here. So we want to get a complete factorization. So now, of course, the 2's will absorb, so we get -2 plus or minus the square root of 6. So this gives us 2 BVs, that is -2 plus root 6. Again, the square root of 6 is larger than 2, so this is a positive number. And the other real zero is -2 minus the square root of 6, which is clearly negative. So now we can do our BVs and write our complete factorization. So -2 minus root 6. Again, the symbolic calculation makes this very simple. We just make sure that we have our order. So now here we have what? X minus -2 plus square root 6, complete factorization, x minus -2 minus square root 6. So again, this makes the analysis very simple. These are just both odd multiplicity. So now, of course, we could just take a 100, and then, of course, both of these factors are clearly positive. And since we have multiplicity 1, we cross in both cases. So we have plus, we have minus, and we have plus. But contrary to the last example, since the radical is not in the denominator, equal to 0 is certainly fine. So we will get a check at both BVs. So now we can see, again, notice the domain of the inner function does not require any restriction. So the intersection is very simple. It's just simply the restriction that we get from analyzing the outer function. So now this implies that the domain of H circle G will just be given by this number line. So we have -infinity to -2 minus root 6, of course, with the bracket, because we now include the BV, union -2 plus root 6 to infinity. So again, we study solution of equations, we study inequalities, and every time we work with functions, we're forced to do those techniques over and over, because in understanding the function, we're in the background using continuity, which is really a calculus concept, but we're kind of forced to deal with it intuitively. We have plenty of numbers for which these functions are defined. I mean, we have plenty of room to move around. But we throw out some numbers, but there's still plenty that allow us to work very conveniently with these functions. So that continuity, having these large sets of real numbers to work with, is very important. Now, just to end, let's just go ahead and write the particular formula here, which of course we're going to see looks very familiar here. So now H composed with G of X by definition is just H of G of X. We'll just write this out. Get another pen. That was about to go out on me. And so we have H of G of X, X squared plus 4X minus 5. So now we have the square root. I'll just write this with brackets, x squared plus 4x minus 5 plus a 3 to the 1/2 power. Of course, we combine the -5 and the 3 to get a -2. So we have x squared plus 4x minus 2 to the 1/2. Now you could see that this is exactly what happens when we do this calculation here. So if we computed our domain of the composition based on this function, we would still end up with this because the inner function does not provide any restriction. Okay, so again, just remember, as you are building a composition from two functions, be sure that you remember the domain of the inner function. And of course, it's not very difficult to build functions, or if you look at this function here, you could clearly go backwards and it wouldn't be very difficult. For instance, we could say the outer function is the square root function and the inner function is just the quadratic. So you could just look at this and define it in a different way. We could just call this function big H of x. And then we could say little g is just x squared plus 4x minus 2. And little f is just the square root function. And so now we could define big H is just f circle g of x. So when you're given a function that is actually a composition, then you have more flexibility. So if we start with this, we can just say, well, the outer function is the square root function, and we can define the inner function as x squared plus 4x minus 2, because that would be the simplest way to do it. And in calculus, that would be exactly what we do. We're going to take the simple route because no need to be difficult. So when you start with a single function and there is the presence of an outer function and an inner function, then you can go to this step and make your single definitions and write the initial function here as a composition. And that's what will be very important in the calculus, especially when we differentiate compositions. So what we're learning now will be very important in the future. So it's often good that we have the college algebra and the pre-calculus techniques so that we are geared and supported in our study of the calculus. Well, again, we will say much more about compositions when we talk about one-to-one functions and invertible functions. And I think you will find that there's a reason why we study what we do in this class. So that's all I have to say about compositions, but there'll be more to come with one-to-one functions and invertible functions. And then, of course, we'll segue into exponentials and logarithms. Thank you very much.